Hi everyone, I'm Chenhui Deng from Cornell. Today I'm going to present Polynormer, a polynomial-expressive graph transformer in linear time. This is a joint work with Chenhui and Professor Zhiwu Zhang. Transformer is increasingly used for graph learning. Particularly, the attention mechanism in transformer naturally learns the global structural information by capturing all pairs of nodes. Moreover, the attention matrix essentially corresponds to a learned graph whose edge weights are represented by attention scores. As a result, the learned graph topology is adaptive to the underlying graph properties such as homophily or heterophily property. However, there are still fundamental limitations of graph transformers or GTs in terms of expressivity and scalability. While prior work has demonstrated that GTs with unbounded layers are universal equivariant function approximators on graphs, the number of GT layers is a small constant in practice, which raises questions about the practical expressivity of GTs. In addition, the attention matrix in GT has quadratic complexity with respect to the number of nodes, rendering it unable to scale to large graphs. To tackle the aforementioned limitations, we propose Polynormer, which is based on a polynomial-expressive base model shown here. Where X represents node feature matrix, B is the bias term, and A is a general attention matrix. By integrating A with graph topology, we have the local attention module in Polynormer. Similarly, by integrating A with node features, we obtain Polynormer's global attention module. Owing to the proposed local to global attention scheme, Polynormer has high expressivity in learning complex functions with a few layers. Moreover, it also has high scalability since the global attention module only has linear complexity. In the following, let's get into the polynomial-expressive base model, which is the building block of Polynormer. Our motivation is that since any smooth function can be approximated by a polynomial, building an expressive model can be achieved by learning high-order polynomials. To this end, we introduce the base model of Polynormer. As shown in the toy example, the base model essentially learns a second-order polynomial that maps the input node feature X into the output node representation Y. Moreover, we theoretically show that an L-layer polynomial learns a 2 to the power of L-order polynomial function. This indicates that with a small l, Polynormer learns high-order polynomials that represent complex nonlinear functions. Apart from expressivity, we also introduce a linear global attention scheme for enhancing scalability. In contrast to prior GT models that involve a large-scale attention matrix with quadratic complexity, we replace the attention matrix with the product of two smaller rectangular matrices. Subsequently, by leveraging the associative property of matrix multiplication, our global attention only has linear complexity relative to the number of nodes. This allows Polynormer scale to large graphs. In our experiment, we compare Polynormer with competitive GN and GT baselines on mainstream datasets. The result indicates that baselines such as LinkX and GOAT, they only perform well either on homophilic or heterophilic graphs. In addition, some GT baselines are not scalable to large graphs due to their massive memory footprint caused by the global attention module. In contrast, Polynormer consistently outperforms all baselines on both homophilic and heterophilic graphs. For more details, please check out our paper and source code. Thank you for your listening.